Okay, solutions are a big deal in chemistry. You've all experienced what a solution is. Most of the time, people think of solutions as something dissolved in water, but it's much more than that. You can involve gases and solids as well. For example, in this room, there are about 5 different gases, and they form a solution of gases. All solutions have 2 parts, a solvent and a solute. Solvents are in the majority, solutes are in the minority. And you can have, there's only one solvent, but you can have 1 or more solutes. Within the solution, we're going to focus on aqueous solutions for this unit. Within the solution, there are 2 forces that are at work that are either pulling the crystal apart or keeping it together. And it's a battle of the forces. One's called solvating force. The solvating force pulls the crystal apart. The crystal lattice force keeps the crystal together. Whatever force is stronger will predominate. Now, we've done the double replacement reactions. We're looking up the whether the new combination of ions forms a solid or not. So when there's no solid or no reaction, that means the solvating force is more than the crystal lattice force. When you form a solid, then the crystal lattice force is stronger than the solvating force. And I abbreviate those by SF for solvating force and CLF for crystal lattice force. Okay, so let's look at we're going to take a polar solvent and a polar solute. Like sodium chloride is a good example of a very polar solute. We're going to dump it in some water. And you all know what happens when we put salt in water, stir it up really well, it dissolves. Okay, so this is what's going on when that happens. So we've got a crystal of sodium chloride there, and we have water around it. Now, water is very polar as well. That means it forms dipoles that have a negative and positive area of charge. And as you know, opposites attract. So what's going on here is we have the positive aspects of the water pulling on that chloride. We have the negative aspect of the oxygen pulling on that sodium. And that's what pulls that crystal apart or makes it dissolve. So we've got at time 0, we dump the salt in. At time 1, this is what's going on. So the sodium cation is being surrounded by water molecules that have pulled it out. And that's called a hydration sphere. So there are primary, secondary, tertiary hydration spheres. Basically, it's the solvent, and usually we're talking about water. That's why it's called hydration sphere. And the water molecules surround the solute molecule. Now, if the solute molecule is ionic, it'll be surrounding a cation, it'll be surrounding the anion. So this would be the sphere right here. That would be the definition of the primary hydration sphere. The secondary hydration sphere would be another layer of water molecules around the primary one. And then the tertiary one would be another layer yet around. So you have primary, secondary, tertiary hydration spheres. The main thing I want you to know in this class is just what is a hydration sphere. So it is what is pulling that sodium ion out, and it's what's pulling the chloride ion out. So you're going to have a chlorine molecule also surrounded by water molecules forming a hydration sphere around that chloride. Okay, and what's pulling that out, again, is the solvating force is very strong in water, particularly if the solute is polar. So you have three situations. You've got a polar solute and a polar solvent like this, and usually those dissolve. You also have a nonpolar solvent and a nonpolar solute like something like gasoline, which is very nonpolar. That's why it floats on water, and pentane. So if pentanes are solvent, we drop a little bit of gasoline in there. The gasoline immediately forms a solution with the pentane because they're both nonpolar. So there's an expression that's called like dissolves like. So nonpolar solvents dissolve nonpolar solutes. Polar solvents dissolve polar solutes. What happens when you have a nonpolar solute and a polar solvent, or vice versa? For example, if we had vinegar and oil, we're making a vinaigrette tonight for salad. What happens when we put the oil and vinegar together? Anything happen? All of you have seen and tasted a vinaigrette. What happens when you just pour some vinegar and oil together in a jar? Anything happen? You're a lively bunch tonight. Who cooks in here? Well, if you've cooked, you've experienced this oil and vinegar bit. What do you do to make a vinaigrette? Huh? Exactly right. So how can you make them mix together? Shake it a lot. And then what happens when you stop shaking? Yeah. So have you made a vinaigrette before? All right, this is one formula for making a vinaigrette. Equal parts oil and vinegar. You add in a little bit of mustard. You add in some breadcrumbs or Parmesan cheese, and you shake it. And it will stay mixed. The deal is emulsifier. An emulsifier will mix a nonpolar and a polar solution together. No emulsifier won't mix. Now, what is an emulsifier? It's usually a pretty good sized molecule that has both non-polar and polar parts. So the non-polar part sticks to the non-polar part. The polar part sticks to the polar part. So in an oil and vinegar situation, the oil is non-polar, the vinegar is very polar. So if we put in a molecule that's got one of each, it's going to be like glue. ¿Cómo se dice pegadura? Glue. It's just pega, not pegadura. Okay, think of it, emulsifier is glue. It grabs hold of the non-polar and the polar molecules and keeps them together. So when you add mustard or Parmesan cheese or an egg yolk into your vinaigrette, it'll stay mixed after you shake the dailies out of it. What's a common emulsifier you use probably most every day of your life? Huh?
Like egg?
Egg yolk. But what do you, that's one emulsifier. It's got lecithin in, which is the emulsifier. I've got a website for you too, by the way. I finally found it. When you are washing dishes, you got a greasy pan and you turn on the water, does all the grease immediately go out of the pan? No, why not? Right. The grease is like oil. The water is polar. They don't mix. So how do you make it? How do you clean your pots? Soap. And guess what soap is? An emulsifier. So when you add soap, that soap molecule, which is mainly made from, well, the traditional soap is made from animal fat, triglycerides. They also have synthetic ones, but that soap molecule has got to have a polar part and a non-polar part. Otherwise, it won't work. So if you dropped an egg yolk into that greasy water, it would probably do a pretty good job on emulsifying the fat. Down the drain it goes. See, I was driving my car. I just got it cleaned. Okay, I'm real picky about my truck. It's a very shiny truck. Okay, I go on a newly oiled road. What happens when I drive on a newly oiled road? What happens to my truck? Huh? I get oil on the side of it because the wheels kick up the oil onto the side of the car, the side of the truck. So when I get home, how do I clean it? Do I clean it with a hose? Would that work? No. I've got to clean it with soap and water because the water is polar, the oil is non-polar. Soap clings them together and washes it off. Okay. Okay, the crystal lattice force does not change. It is a constant. However, the solvating force does change. Okay, let's go back to our oil and water. Get a greasy pan in the sink. What's the best way to get rid of the grease? With cold water or hot water? Hot water. So the solvating force, one of the factors in the solvating force is heat. What else? If you have a cup of coffee, you're putting sugar in. If you stir it, does it dissolve faster or slower? Faster. So physical agitation is another variable for the solvating force. And there's one more that is kind of tricky. If I have two forms of sugar, I have a big piece of rock candy, which is a big crystal of sugar, and powdered sugar. I put a tablespoon of rock sugar into the cup of coffee versus putting a tablespoon of powdered sugar in the coffee. Which dissolves quicker? Powdered sugar. What's the difference between the powdered sugar and the big crystal of rock candy? Surface area, exactly. So the surface area is another variable for solvating force. So these are all so these are directly proportional and that's what that open infinity sign means. So when one goes up, the other goes up. So if we increase the heat, solving force increases. If we increase the physical agitation, solvating force goes up. If we increase the surface area, solvating force goes up. So if you have your good old cup of coffee here, you have three ways of making that sugar dissolve faster. Heating it up, using a spoon and mixing it up really well for the physical agitation, and also using a finer sugar in there with more surface area. Now, all three of these let's look at a crystal of sodium chloride. Now, the way that sodium chloride is dissolved is water molecules will hit it. And then if it hits it and there's an attraction, when it comes off the crystal, it will pull the sodium ion with it. So all three of these are related to how often can I get that water molecule to bump against the crystal? Okay, because it's a surface phenomenon. That's why when we increase the surface area, we increase the surface area so the chances of it bumping into that salt crystal are much higher. So one way, what is one way of measuring heat? You all know this. How do you measure heat? Thermometer. And what does the thermometer measure? Temperature. So the metric for heat is temperature. So as the temperature goes up, the speed at which the molecules will hit that surface increases. Okay, so temperature then okay, everything moves. This thing moves, my hand moves, everything moves. And it moves at a certain temperature. As we increase the temperature, the movement of those molecules will increase. If we bring the temperature down lower, it's going to slow down. We go lower, slow, slow, slow until we stop movement. That's called absolute zero, when there's no molecular movement. Okay, so solvating force is a variable. It can vary with temperature, physical agitation, and surface area. Crystal lattice does not. So we can affect whether that dissolves or not by changing the solvating force and getting the solvating force greater than the crystal lattice force. Once the crystal lattice force is diminished compared to solvating force, it dissolves. And it's hard to predict. When we put sand in water in a beaker, what happens? Nothing. That's right. Sand doesn't dissolve in water. So which is greater, the crystal lattice force or the solvating force? Crystal lattice force. That's right. When we put salt in water and dissolves, which is greater, crystal lattice force or solvating force? Got the idea? What would it be? Putting salt in water and the salt dissolves. Which is greater, the solvating force or the crystal lattice force? Solvating, right, because it dissolves. Solvating means it tears it apart. So if something doesn't dissolve, that means crystal lattice force is greater than solvating force. But if we increase the temperature, that increases solvating force up to the point where it becomes greater than the crystal lattice force, it dissolves. So the thing you can control is solvating force, not the crystal lattice force. Okay. So you need to be comfortable describing these situations. You will have a question on test 5 regarding this. Qualitative solutions in terms of solute, solvent, solvating force, crystal lattice force, the parameters for solvating force. Guaranteed, okay? All right, now this is a qualitative aspect. Notice I haven't put any numbers in yet. There's a quantitative side to solutions as well. All right, so are there any questions about this guy here we talked about so far? Okay, all right, so let's now go over to the quantitative side of things. So whenever we say quantitative, that means mathematical. So okay, so how do we measure solute in solution? Now, all of you are familiar with the word concentration. Something's more concentrated, there's more solute compared to something that's not concentrated. So what is the common unit we've been using in this class so far? Moles. Guess what? Okay, so molarity is moles per liter of solution. And the solution includes both solute and solvent together. And that's called molarity. So whenever you see when we go to the lab tonight and Thursday, you're going to see everything in there has got a big M, uppercase M. And that'll tell you the concentration of that solution. There is another way of measuring quantitatively the concentration, and that is moles of solute over kilogram of solvent. And that is used a lot in chemistry, and that is called molality. And it's an uppercase, excuse me, it's an italic M. Now, we're not going to be using this in this class. When you go to 1A, you'll use it a lot. We're going to be focused on, in this class, molarity, not molality. Molality comes into play, something called colligative properties. So the reason why you salt your sidewalk when it gets frosty out there, it's because of molality. Because what happens is when you add salt to water, it freezes at a lower temperature. It also boils at a higher temperature. Some people used to think that's why they added salt to water when you cook pasta, because it boils at a higher temperature. It does boil at a little bit higher, not enough to make any difference. The reason why you put salt in water for pasta is for seasoning reasons. Okay, now we're not going to talk, that's all I'm going to say about that. 1A, there's a lot of stuff about molality and colligative properties, but you have to wait till you get to 1A. All right, so molarity. So let's do an example problem. All right, so I've got 5 grams of sodium chloride and 3.1 liters of water. What's the molarity? Remember the definition of molarity, it's moles per liter. Grams, we need to convert to moles. And I need to find a periodic table. I'm going to pull it to here. What is that? Yes. So that's what we have to calculate. So you're going to divide 5 by 58.44 and divide it again by 3.1, and that'll be the moles per liter of that solution. So that would be 0.28 moles per liter. Okay, so let's do a bunch of examples here. Now, there are two ways to do these kind of problems. One is dry, the other is a wet solution. Okay, I'm going to focus on the dry right now. Okay, so this problem here is, let me move that off there. All right, make up the following solution. The directions, just like we do in a lab. How would you make a 2.1 liter solution of 5.0 molar NC salt, NaCl? Okay, so remember, and that's equal to 5.0 1 liter. Okay. So if we're going to make it up, you need to know how many grams it is. So we need to convert the 5 moles to grams. First thing. And then the next thing we need to do so this will give us grams per liter. Well, we don't want 1 liter, we want 2.1 liters. So we're going to multiply that answer times 2.1 liters. All right. So the directions are it's actually 610, not 614, because I have 2 sig figs. Okay, so we're going to add 610 grams of sodium chloride to something less than 2.1. This is critical. Now, the reason why you don't add it to 2.1 liters is because of something called Archimedes' principle. When you sit in a bathtub, what does the water do? Does it go down? It goes up, right? So your volume increases when you sit in the tub. So that's why we can't put all 610 grams of sodium chloride in 2.1 because it'll no longer be 2.1, it'll be more than 2.1. So what you do is you dissolve it in something less than 2.1. Anything less, it doesn't really matter. It could be 1.5, 1.6, 1.7, it doesn't matter. Get it totally dissolved, then you bring the water up to 2.1. Okay, does that make sense? This is a very standard question, is they will ask you how to mix up a solution. And this is the right way to go. Just don't say you add 610 grams into 2.1 liters, because you'll no longer have a 5.0 molarity solution. You'll have less because the volume is more. You have like 4.9 or whatever, okay? So what you do to dissolve the solid first in a little bit of water, something less than the final volume. It doesn't matter at all. And then it was totally dissolved. We just did this in my 1A class at Sac City, exactly this. And half the class didn't know how to do it. So I explain this exactly this problem here. Okay. Okay, so that's a typical problem. How do I make this stuff up? You need to know the molarity and you need to know the volume to make it up. Similar problem here. Go ahead and do this one. Try this one yourself. And it's 58.44, the molar mass. This was going to be done exactly the way we just did that problem prior. In this problem, what's the key to start? Yes. We want to start with a molarity, 2.34. And instead of a big M, we're going to say moles per liter. Now, there's two ways to work this problem. One way is to convert the 2.34 moles into grams, then multiply by the 7.18 liters, or you can multiply by the 7.18 liters first and convert the subsequent moles to grams. So let's do it like the other problem. So we're going to multiply let's get our grams first, and then we're going to multiply, and this would be for 1 liter, but we want 7.18 liters. Oh, got around. So we have to dissolve the 982 grams of sodium chloride in something less than the 718 liters. It can be 7 liters, it can be 6 liters, it can be 1 liter, it doesn't matter. When it's completely dissolved, bring up to final volume. Okay, so that's one kind of problem. We're asked to make up a solution. Interestingly, during a interview question, this school, when they interview a professor, they do it in both orally and also in the lab. So this is one problem they always give you. They'll say, make up a 2.1 molar solution of this. And they watch how you do it. Okay, so that's one type of dry problem. Another problem is, let's see here. Do I have one example? Another one is I tell you, we throw in 3.45 grams of dry sodium chloride into 23.4 liters of water. What's the molarity? What's the final concentration? Okay, so it's kind of the opposite of that other problem. So here we would start with, remember we want to end up with moles per liter. So the first thing we need to do is convert that 3.45 grams into moles. And then divide that by our volume, because it's moles per 1 liter, not 23 liters. So we're going to go 3.45 divided by 58.44, divided again by 23.4. So 0.00252 or 2.52 times 10 to the minus 3 moles per liter. Again, the focus is moles per liter. So if we're starting with grams, you got to convert to moles. If we're starting with the molarity, then we take the moles to grams. It's just the opposite approach. Okay, let's do another one, and then I'm going to go on to wet. Okay, let's just do this. 13.45 grams in 3.4 liters of water. What's the final concentration? Go ahead and try that on your own. See how central moles are in chemistry? Mole everything. Okay, the way we're gonna work this is we're gonna take the grams, convert to moles. Then we're gonna divide by the volume we have to get it down to 1 liter. So we're gonna go 1345. That'll give us moles of salt all over 3.4 liters. How many sig figs is our answer gonna have? 2. So it'd be 6.8 times 10 to the minus 2 moles per liter, or 0.068. Okay, so there's some, I put a bunch of worksheets in Canvas under files. Practice this. Now, what I want to do is give you a flavor for the wet side of things. The most frequent wet molarity problem you run into is taking a concentrated solution and diluting it down to whatever the concentration you want is. Frequently, when we buy acids and for the stock room, we buy them concentrated and we dilute them down to what we want. It's cheaper that way because they don't have to ship water around. Okay, so to do this, it's kind of in 2 parts. Concentrated is in a moles per liter, and the dilute is in moles per liter. So for example, problem could be okay, what's the final concentration if we added 1.23 liters of 3.45 molarity sodium chloride to 12.3 liters of water? Okay, so without much calculation, what's our final volume? Is it 12.3 liters? What's our final volume? If it's not 12.3, it must be, yeah, we just add them together. So it'd be 13.53. That's our final volume. Okay, now I want you to notice something here. If I have 3 molecules of salt sitting on the bottom here and 1.23 liters of water, and I put in 12.3 liters more of water, how many salt molecules do I have? Do I have less salt molecules, more, or the same? The same. What then is we've increased the solvent. We haven't touched the solute. Solute is salt here. So if we start with 3, we're going to end with 3. If we start with 2 moles of salt, how much salt do we end up with? 2 moles. So the solvent changes, but not the solute. So that means we can say okay, so moles concentrated equals moles dilute. And the converse is true also. Moles of dilute equals moles of concentrated. The only thing that's changing is the volume. Okay, so we can calculate the moles at what we started with. Okay, we started with 1.23 liters of 3.45 sodium chloride. Okay, 1.23. How do I get moles if I know the molarity? 3.45 moles per 1 liter. How do I know how many moles is in that concentrated solution? What do we need to multiply the 345 by? No, what do we multiply this by to get just moles? This is unit 1 stuff, dimensional analysis. What do we multiply this by to get rid of the L? The liters, right? And how many liters are we talking about concentration-wise? 1.23. That's equal to the moles of our concentrated sodium chloride solution. Okay, over here, let's see, let's do this different. So we have 345 moles per liter times 1.23 liters. That gives us moles. Over here, remember, that's molarity, so it's moles per liter. We multiply moles per liter times liters, we end up with moles. So now we have to solve for M. So Liters cancel, gives us moles per liter, which is molarity. So the molarity of that solution after we diluted it is 0.319 moles per liter. So on Thursday, I'm going to continue some more examples of the wet, and then I'm going to combine the wet and the dry together. For example, if I have a 3.68 liters of 2.8 molarity salt solution, I dump it into one that's got 5.8, what's the final concentration? Yeah. What did you get? Oh, yeah. I divided by 13.3 instead of 13.53. You get 314. Now, had that been a test, I would have given 9 points, 90% credit for this. And with the wrong answer, you'd have lost 1 point. Okay, because your setup is correct, even though I can't put my numbers in right. Okay, so I'm going to leave you with this for Thursday. So I'm glad you guys came today, because Thursday is going to be horrendously confusing if you've never done this before. Because we're going to now combine on Thursday the dry process and the wet process. I'm going to start off with doing a lot of more wet problems. Then we're going to combine them together. Okay. Correct.